In this video, I'm going to go through the solution to a practice problem, and hopefully you've had a chance to try it already. If not, pause the video and give it a try. What we're looking at here is trying to list the possible hybridized atomic orbitals that an element can have. And so the ones that occur for any molecule for that element will depend on what it's bonding to. So these are just kind of like the possibilities for this element. So I've written under each of our three elements we're going to look at their electron configuration to kind of shape this discussion. And starting with helium, it has a 1s2 electron configuration. So it has two electrons, they're in the 1s orbital. But we are only occupying the n equals 1 energy level, which only has one s orbital in it. So that means that the only possible orbitals for helium are just s. Like it can't hybridize with a p orbital because there are no p orbitals in the n equals 1 energy level. And so that's it. It doesn't actually hybridize at all. So helium and hydrogen can't hybridize their orbitals because they only have one. All right, so then moving on to boron, which has more electrons, so it'll be a bit more interesting. So I'm going to focus just on the valence electrons because only our valence electrons are going to hybridize because they're going to participate in a covalent bond, but the core electrons won't. So looking at this, I'm in the n equals 2 energy level, and so that means I can have s and p orbitals only. Remember, we can have as many different shapes of orbitals as n minus 1, right? So this will be 2 minus 1, so that, or sorry, the number of nodes. So we would have our L value would be equal to either 0 or 1. And so that's going to correspond to S or P. So with working with only S and P orbitals, we can hybridize an SP. SP squared. I can bring in 2 of my p orbitals, or I can bring in all 3 of my p orbitals and make sp3 hybridized. So I can make these 3 hybridized orbitals for boron and nothing else. All right, moving on to silicon, I'm going to highlight my valence electrons, and I have I'm in the n equals 3 for my principal quantum number. So that means L can equal 0, 1, or 2, which is going to correspond to S, P, or D orbitals. So while my valence electrons for silicon only occupy the S and the P orbitals, that energy level 3 has D orbitals in it. They don't have any electrons in them, but they exist. And so I can actually use those D electrons. So at n equals 3, I have S, P, and D orbitals that I can use. That means I can have sp hybridized, I can have sp squared, sp3, and I can start bringing in my d orbitals like sp3d, sp3d squared, and this can continue to incorporate all the d orbitals, although that'd be extremely unstable because it would be so crowded around that atom. We're only going to focus up to the octahedral shape for our hybridized orbitals. So we don't need to go past sp3d squared. But you can imagine if you bring in a third d orbital and hybridize, then you would be able to create 7 different bonding orbitals. And that's a structure that exists for a really large central atom. You can fit 7 things around it, even 8 if they're small enough. And so we can continue to use them. Won't go into detail about it because they're so uncommon in this class.